Alrighty guys, welcome back to my virtual classroom. This is going to be lesson 4 of our distance learning. Today's topic is refraction and Snell's law. Okay, so if we take a look at this objective, we're going to be looking at a phenomenon known as refraction, dispersion, index of refraction, and critical angle. We're going to be looking into what it means to say something has an optical density, which will make sense a little bit further down the road here. And again, that term index of refraction. So a couple new physics words, and I'll have a couple little video clips that accompany this that'll help make sense of a lot of the stuff I'm talking about here. So if you're taking notes, we're someday in April right now. I'm not sure what it is because these are pre-recorded, and refraction of light is our main topic. Okay, so take a look at these pictures I have up here, like a diamond. Why are diamonds so expensive, popular? Why do they have this vibrant sparkle to them? Or why, if you look at that straw, or if you stick a pencil in a glass of water, it looks broken on the inside, right? And then even if you're driving down the road, especially on a warm day, you look up ahead of you and it looks like there's water. Why do you get that mirage? Well, the answer to all of this is refraction. So let's take a look at refraction and see why it is so key to all of the phenomena I just showed you in these pictures. Okay, I'm going to show you a quick video demonstration. If we were in class right now, you guys would be doing this on your own, but I'm going to do it for you. So we're going to jump right into the video and I'll explain it to you in the video. Okay guys, in order to demonstrate refraction, I've done a little pre-work here. I have an acrylic block, which is basically a transparent piece of plastic, and as you can see, you can see right through it. I've also placed it on this piece of graph paper before we started the video, and I drew a box around it. And then I also drew 3 normals, perpendicular lines to where the piece of acrylic is going to be. And on this one, I made an angle of 20 degrees for my first, what I'm going to call incident ray. Then this purple ray is 40 degrees, and it'll be the second incident ray we look at. And the third incident ray is drawn in red, and it's going to be 30 degrees. So to demonstrate refraction, which is how light slows down when it enters a new medium and then it speeds up when it leaves it, or vice versa, I'm going to use this piece of acrylic. So we're going to set the piece of acrylic on top of the piece of paper, and you can still see the incident lines that I drew. And here's a laser. I'm going to turn on this laser so you guys can see the beam. And the first incident ray, I'm going to just put it right at the ray that is drawn 20 degrees to the normal. And as you can see, it enters the medium, it enters the acrylic, and it exits on this side. So I'm going to pick up the green marker, and I'm just going to put a dot here and a dot here for that beam. So that's the green beam. And so the beam went in, it slowed down when it was in the acrylic, and then when it slowed down, it left the acrylic and it sped back up. So I'm going to go ahead and bring it over here to the purple incident beam, which is 40 degrees to the normal. And you can see it also goes in and it exits. And I'm going to grab the purple marker and make 2 dots right on that line so I could redraw it later. And I'm going to do the same thing with the red incident beam, which is 30 degrees to the normal. Slide it there. And pick up a red marker. Put a dot there and there so you can see that. Okay, now I'm going to go ahead and turn off the laser. I'm going to remove the acrylic block, and I'm going to use a straight edge. I'll just use this drafting triangle, and I'm going to connect the green beam that left the acrylic, the 2 dots there. I'll draw an arrow on it to show that's the direction it was traveling. I'm going to draw the purple beam that exited the acrylic. Bring it just right up to the piece of acrylic, like so. You can see that's where that beam left. And finally, I'll do the same thing with the red beam. And that's the beam that left when it entered at 30 degrees. Now, one thing I do want you to see before I connect any lines here, check it out. We'll start with the red one. Notice how the exiting beam is perfectly parallel to the incoming beam. Notice how the purple beam is perfectly parallel to its incident beam, and the green beam is also perfectly parallel to the incoming beam. So, as you can see, they didn't line up from where they entered to where they left, right? It slowed down when it entered the acrylic. The light slowed down when it entered the acrylic. And now I'll go ahead and draw how much it was bent when it slowed down. It actually entered. It bent towards the normal. See the normal right here? It bent towards the normal. And then it sped away when it left. So there you can see the green beam. Purple beam did the same. The incident beam came in. It bent towards the normal. And then exited. And the red beam, which entered at 30 degrees to the normal, as it came in, again, they all bent towards the normal, right? So that means they slowed down when they bent towards the normal. And you can see how much the lights, each beam was bent as it went in there. I'm going to go ahead and measure these angles. And then I'm going to record them on the sheet of paper. So you can see this paper right here, angle of incidence for the green beam it was 20. For the purple beam it was 40 degrees. And for the red beam it was 30 degrees. So I'm just going to take this protractor, line it up on each of these beams so we can find out what the angle of refraction was. For the green beam, the angle of refraction was looks like about 13 degrees. So the green beam, actually, I'm going to write it right in here. Then I'll put it on the paper later. 13 degrees. We'll say that is R. R equals 13 degrees. For the purple beam, our angle of refraction looks like about 24 degrees. R equals 24 degrees. And finally, the red one, it entered at 30 degrees. It was bent towards the normal at an angle of, let's say, 19 degrees. R equals 19 degrees. So to finalize this data collection, right here, R for the red beam was 19 degrees. For the purple beam, R equaled 24 degrees. And for the green beam, R equaled 13 degrees. There you have it. And we'll take a look at that when I get back to the PowerPoint. Okay, so after looking at the video there, I had three angles of incidence at 20 degrees, 40 degrees, and 30 degrees. And the refracted angle when the light entered that piece of acrylic was for the green beam 13 degrees, for the purple beam 24 degrees, and for the red beam 19 degrees. So now we're just going to take the ratio of the sine. So on our calculators we're going to use the sine function, and it'll be the sine of the angle of incidence divided by the sine of the angle of refraction. So on the first one, if we take the sine of 20 and divide that by the sine of 13, we come up with the number 1.5. If we do the same thing for the purple beam, the sine of 40 divided by the sine of 24, we come up with another number, 1.5, which is actually the same. And then if we take a look at the last one, the sine of 30 divided by the sine of 19, it also comes out to be 1.5. So that number right there is pretty significant, and it's significant to acrylic because acrylic is defined as having an index of refraction of 1.5, which, as you can see, is just a simple ratio of the sine of its angle of incidence to the sine of its angle of refraction. So what does this mean? Let's go ahead and take some notes. Just jot down these key ideas I'm about to show you. Then we're going to have a book assignment on this principle, and that'll be our lesson for the week. So, first of all, this is what your notes will look like. We're going to talk about these, 5 topics. So you might want to, if you're taking notes, which I hope you are, just write down one at a time as they pop up and just jot down some of the key concepts that you see in this presentation. Okay, so let's start off with refraction. As is pretty obvious from the video, refraction is defined as the change in speed of a wave, either light or sound, because sound waves can also be refracted, when passing from one medium to another. So, pretty straightforward definition. A wave enters one medium from another, and it'll either speed up or it'll slow down, and that's what we call refraction. If you take a look at a prism, I think most of us have seen them sometime in our life, maybe in a past, like middle school science classroom. It's this triangular piece of glass, and when light enters it, you get this spectrum of colors: red, orange, yellow, green, blue, indigo. It's controversial whether we use that anymore, and violet. So you notice all of these beams, what started out as white light gets divided into all of its separate colors, these frequencies of colors, when they enter the prism. So frequency has something to do with refraction. White light, as we know, is a mix of all those colors, and those colors all get divided when they enter the prism because of the fact that they slow down when they enter. So if we take a look here at a diagram of a prism, you'll notice the white light coming in. Find my pointer, there it is. That white light comes in, and as it comes in, notice red and notice violet. So which one is refracted the most? As you can see, I'm going to put I'm going to go ahead and throw a normal on there. When that white light enters, all of these different frequencies bend towards the normal. Here's our normal. As they come in, they don't go away from the normal, they go towards the normal. And you can see the one that is refracted the most is the highest frequency wave, which is violet. So this whole process of breaking up white light into all of its different wavelengths, frequency and wavelengths, is called dispersion. The higher the frequency waves of white light refract more while being transmitted through the crown glass of the prism. The lower frequency, like red, is refracted less. Okay, so the next term is index of refraction. The symbol for index of refraction is N. And index of refraction is defined as a transparent material's ability to bend light. So in that picture I showed you earlier, we had a diamond on there. Diamonds have a really high index of refraction. It's like 2.4. I believe it's something like that. We'll see here in a second. That piece of acrylic that I showed you in the earlier video, it has an index of refraction of 1.5. So all materials have this different ratio, which is their index of refraction. and that's what gives them their optical properties. Diamonds, they capture light and they bend it quite a bit, and if you cut a diamond and you're pretty skilled at it, you can actually have that light go into the diamond and be refracted internally, something we'll call total internal reflection, which I'll show you here in a few moments. So here's some examples of refracted light. For a vacuum, like in space where there is no air, we say the index of refraction is 1. Now if you look at just regular air in our atmosphere, it's 1.00002926. So whenever we're doing calculations with air, we treat it as if it's a vacuum. Water, in the form of ice, has an index of refraction of 1.31. Regular water, 1.33. There's glass, there's different types of glass, so 1.47 to 1.52. Acrylic, there's the one that we did the lab on, 1.5. And you can see down there it is, diamond 2.4. So diamond slows down light the most when it enters it. It has a really high index of refraction. Okay, just to give you a better visual, if I had all of these different materials lined up, let's see, we have air up on the top. So in this visual, here's my pointer. We'll say this is air or a vacuum, and then these are 1, 2, 3, 4 different materials, and then that top material is there. Let's see what happens to this beam of light as it enters all of these different materials. So I've drawn a normal here. As that light enters, it goes from 1.0 to 1.7, so it is going to slow down and it'll bend towards the normal, not away from the normal. So always remember that. When light or sound enters a different medium that is more dense, in this case with light optically dense, it'll always bend towards the normal. So if I click that on there, you'll notice the beam of light that just came in there, it bent towards the normal. Okay, so you see if it were to go straight like that, it wouldn't bend, but when it did bend, it slowed down, so it went towards the normal. If I go ahead and click on another, put another normal up there, this one goes to 1.0, so would it go towards the normal or away from normal? It's going from more optically dense to less optically dense, so now we can see that it is going to go away from the normal. Again, I'm going to hypothetically use my pointer. If it went straight, it would go like that. If it went towards the normal, it would go that direction, but it is going away from the normal. So hopefully you're getting that idea. If it speeds up, it goes away from the normal. If it slows down, it goes towards the normal. So here it goes from 1.0 to 1.2. It's going to have to go towards the normal. So very slightly towards the normal. 1.2 to 1.5, again, it'll go towards the normal because it's slowing down. Okay, 1.5 to 1.7, again, slowing down, so towards the normal. But then it goes from 1.7 to 1.0, so it'll now speed up and go away from the normal. And just like I showed you in the lab, the entering beam, the incident beam right here, would be parallel to this exiting beam here. They would both have the same angle from the normal. All right, so hopefully that makes sense. I'm going to go ahead and show you another quick demo. I call this the disappearing beaker, using 3 different optically dense materials: Pyrex glass, water, and the mystery one, I'll just go ahead and tell you what it is now, baby oil. So, enjoy. Okay, so far in our lesson, we've learned all transparent materials have an index of refraction notated by the letter N. Okay, so what I have in front of you here are some beakers, and these beakers are all made out of Pyrex. It's a special glass that is heat resistant. And Pyrex has as you can see, it's transparent. All of these are transparent. It has an index of refraction of 1.74. So 1.74, 1.74, 1.74. Inside this container, I have water. Now, water is not as optically dense as Pyrex. Water has an index of refraction of 1.33. And then I have baby oil. Okay, and this baby oil here is also transparent, and we'll find out what its index of refraction is in a second here. So I like to call this the disappearing beaker. Let's see if we could make this Pyrex beaker disappear when we fill it with water. So, as you can, hopefully you can see the container. I'll put it up so it's easily viewed. As I pour the water into the Pyrex, can you still see the Pyrex glass? And obviously you can, right? The air out here has an index of refraction of 1, we'll say. So 1, and this has an index of refraction of 1.74, and that has an index of refraction of 1.33. So they all have their own specific index of refraction, or indices of refraction, so we can see them individually. So I'm going to go ahead and hold this up, and let's see if it makes any difference when we fill up the little beaker and let the water pour over it and into the larger beaker. And there you have it. Both beakers are it's very obvious. You can see the small beaker inside there. All right. So nothing too fancy there. I'm going to empty this water out. I'm going to put this little beaker to the side. And by the way, that was Pyrex. And this one right here is also Pyrex. I'm going to dry it. Take this water to the side. And I said earlier, this Pyrex beaker has an index of refraction of 1.74. Well, it just so happens baby oil has an index of refraction of 1.74 also. So I'm going to take Pyrex beaker. Now there is writing on it, so you'll be able to see the writing. There's writing on this one also. I'm going to set the smaller beaker inside the larger one. As you can see both beakers. But now I'm going to take this baby oil, which has the exact same index of refraction as Pyrex, and let's see if we can suddenly make the internal beaker disappear. So watch as I fill it. Right there you can still see it. It's full of a liquid. And now we'll let it pour over the top. And as you can see, that internal beaker disappeared because they both have the same index of refraction. And cut. Now I'm going to show you a kind of a cool trick you could try at home, pinning a cup. Go ahead and watch this little video clip and maybe try this with somebody in your house while we're doing this social distancing. So a fun activity you could do at home is get something like a coffee cup and stick a penny at the bottom of it. Now you want maybe put some modeling clay or something or a piece of gum to make the penny stick to the bottom. And then have somebody in your household look at the penny and then slowly walk backwards until the penny just goes out of sight, as is demonstrated by the camera. So now you can't see the penny anymore, and the light that's bouncing off of the light in this room and going into that penny, it's hitting the penny, but it is not making the angle to get to your eye. The way I could get that penny's light to get to your eye is I just have to add water to it. When I add the water, the light that is leaving that penny will leave the water and bend now away from the normal, because air has a lower index of refraction than water. So it'll bend away from the normal and go right up into the observer's eye. Let's see if it works. And there you have it. So try this at home. Have somebody walk up to the glass and then slowly walk backwards. And as soon as they can't see the penny anymore, have them stop. Then fill the cup up with water and voila, they'll see the penny. Okay, let's finish up our notes. Critical angle and total internal reflection. Well, first of all, critical angle is defined as when the incident ray coming in within a medium, when the incident ray is in the medium, it causes the refracted ray to bend at 90 degrees perpendicular to the normal. So that doesn't make much sense when I just read it to you. So let me show you an image. If we take a look here, I'm going to get my pointer on there. All right, so right now we have light inside this glass. So let's suppose there's a beam of light inside the glass. If that light of beam is in the glass, it's more optically dense. So here's the incident beam from the normal. We'll look at the green one. It's going through the material. Then as it leaves, it goes into air, which has an index of refraction of only 1.0, so it bends away from the normal, like I was talking about earlier. Okay, that makes sense. But now if we increase this angle, see we have theta sub c? If we increase this angle to a point where now that refracted beam that comes out, it's still going to bend away from the normal, but it's bends so much that it is now 90 degrees from the normal. And that's what we call the critical angle of a beam of light. Okay, so the critical angle is the angle at which the incident ray is refracted at 90 degrees to the normal on the outside. Okay, and then you get, if you increase that angle even more, which is depicted by this blue line, not only does it bend away from the normal, it goes all the way back into the medium it was traveling in, and that's what we call total internal reflection. When I was talking about the diamonds earlier, that's what makes an incredible cut for a diamond, when you could cut it at such a way that when the light enters it, it gets trapped basically inside, and you see the glistening in the diamond. So total internal reflection is basically when you go past the critical angle and light it goes in and it gets scattered inside the medium. Okay? So right there, the red part was what we called that angle. Let's suppose that was like 57 degrees. That would have been the critical angle for that material. Okay, and the last one, law of refraction. This is also known as Snell's law. That's basically what I did the lab on. It's the index of refraction of a material is equal to the ratio of the sine of the angle of incidence to the sine of the angle of refraction. So those words put into equation form is basically what I showed you in the lab. To get the n, or the index of refraction of a material, you just take the sine of its angle of incidence divided by the sine of the angle of refraction. And that is the equation for Snell's law. N equals sine of I over sine of R. Okay, so now if you read page 561 to 562 in your text, it basically explains everything I just showed you. There's some questions I'd like you to answer on page 565, numbers 1, 3, 4, 6, and 7. So just do those. Honors students, on page 563, you could read a little bit there about how to find the actual angle instead of n. And just do number 9 on page 561. All right, folks, I'll be at my office during office hours. Send me an email anytime if you have questions, and I will see you next time.